In this video lecture, I want to talk about the finite potential well. So, to get this started, let's recall an earlier example that we've covered on this channel, and that is the infinite potential well. That looks like this. So, as we can see, the potential energy here is infinite. Therefore, this represents a particle within a system that is confined in region 2 such that you can only find it between the intervals of 0 and L because, like again we said, the potential at the boundaries are infinite. Now, what if we change something about the potential energy? What if for the barrier, instead of it being infinite, we make it finite by just giving it some arbitrary value u naught? Well, there is a big consequence to this, and that is that particles have a non-zero probability of existing in all regions. All right, don't be fooled though. The probability of finding a particle is still low in regions 1 and 3, but you can still find it. It's low because there's still an energy barrier, right? But the energy, you can find it because the energy barrier is finite and not infinite, like what we've seen in our last examples. And as we increase that u naught, as we increase the potential energy to infinity, u equals infinity, the probability in these regions, 1 and 3, will approach 0, turning it into the familiar scenario of the infinite potential well. So let me write that down for you. So basically, this says that as we increase the potential barrier to infinity, the probability density, or as we interpret, the probability of finding a particle is equal to 0. And for this to happen, the wave functions at regions 1 and 3 will also equal 0. Classically, how can you think of a finite potential well? Consider this example where you have a box. All right, region 1 is to the to the left of the box, 3 is to the right, and 2 represents the volume of the box. Okay, if you have a particle within this box, so region 2, there's a chance it'll, for a lack of a better term, pop out and can be observed outside the box. So you had something that was originally in here, it can just kind of just pop out. Now, this is incredibly unintuitive if you consider particles as purely particles. You know, in quantum mechanics, we can't think of it like that anymore. In this scenario, they exhibit wave behavior, i.e., waves can go through walls. So this is not a perfect analogy, but imagine you're in your room and you closed all the windows, the doors, etc., to block out sound from the outside. And even if you do that, there may be a small possibility you hear a faint, muffled sounds. So it'll kind of look something like this. So imagine to the left of this wall is the outside, and to the right is your room. So as you can see, we have a very high frequency sound wave. Um, so it's very high pitched and loud, but as it enters when it goes through the walls, um, the wavelength decreases. The wavelength increases and the frequency decreases. So the sound is much more lower intensity, and it's gonna be um, less loud compared to if there wasn't a wall in the first place. So, how do we, I guess, model this behavior? Um, the small non-zero possibility on the left and right side edge of the box. To put it simply, the wave functions are going to be uh, exponential in nature. So, for instance, you will probably have something like this. Yes, for exponential functions, you can see that I kind of drew it poorly here, but it actually doesn't go to zero. It just approaches it very, very quickly. And this is very good because it gives you a small area, or as we interpret it, a small probability of finding a particle. And you may not have catched it, but I noticed that I have said wave functions with an S. We're going to need multiple to describe this quantum behavior as well. So putting it all together, um, we'll see something a bit more unorthodox. So let me make some space. Okay, so so if we were to graph the probability densities of each respective quantum system, the finite potential well and the infinite, we would see something like this. As you can see here, it's not the best visual example, but this on the very left side, we see an exponential increasing behavior. So it could be modeled by like e of x, and we see a decreasing one here. So like e of negative x probably. And here we see a parabolic behavior, similar to the one we see on the infinite. So as you can see, we have to basically come up with three different functions for three different regions, whereas we only have one function for one region here. Now, you might say this is pretty bad, but it could be worse, as we can probably reuse our old wave function that we've derived in our last lecture. But no, we can't. If you inspect the probability function for the finite potential scenario, we can see that it doesn't drop to zero. It doesn't drop to zero at x equals 0 or x equals L. It just keeps decreasing past those values. which is so they're completely different functions. The wave function we derive from the infinite one, it does not match with the finite one. So as a result, we have to derive a whole new set of functions. And as a result, this is, pun intended, exponentially more difficult. Not to mention, we also have to somehow find a way to connect them, the functions at regions in regions 1, 2, and 3, somehow connect them to each other uh, through boundary conditions. Now, as of now, you're probably a bit overwhelmed, and consequently, there's probably not going to be a follow-up video dealing with the mathematics unless you guys really want it. Um, so moving on, what's the significance of this? So, like this now, this this behavior of bypassing barriers, despite not having energy, is called quantum tunneling. That's the significance. And there are a lot of examples you can go through, but I'll explain one about radiation, which I'll detail in the next video. So stay tuned for that. But just to leave you with other examples, one could be about the sun. The reason why the sun glows is because of quantum tunneling. Fusion doesn't happen at the temperature in which the sun is currently at. Here on Earth, we conduct fusion at way hotter temperatures. But since the sun has so much fuel, they're able to bypass quantum barriers just because there's so much instances of that happening. All right, so stay tuned about the for the quantum tunneling example about radioactivity.